Okay, so last we left off, we were talking about physical versus chemical. Is that right?
Yeah.
We all did our voting. You guys understood it. You're feeling confident?
A little bit.
Getting
A
there.
little bit. I want to hear like, yeah, I got this, right? Okay, so let me ask you. We'll test the waters a little bit here. So, let's say your car rusting. Is that a chemical reaction or is that a physical reaction?
Chemical.
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 Okay. Let's see. What about copper wire conducting electricity?
Physical. Chemical.
Chemical?
Because if it burns, you're not getting anything back. Or like if the electricity.
Well, if it's conducting electricity, there shouldn't be any burning going on.
Oh.
Is it?
Was a chemical reaction?
Is it a
I
chemical?
missed the question. Yeah, I think
I
it's
said,
physical.
I said copper wire conducting electricity. Is it physical or
Physical.
chemical?
Physical.
It is a physical reaction because at the end of the day, you're getting the copper wire back. Nothing's happening to
Oh,
the copper
gotcha.
wire, right?
Mhm.
Okay. So you got it?
Somewhat.
Okay. So don't worry, because we're going to do an experiment on it here once you guys get all your stuff for your kits.
Okay.
Okay.
Yeah.
And we'll test you even further on that. Okay, so let's talk about pure mixtures. Okay, so something that is considered to be pure, it means that there's only one of that type in it. Like for instance, we could have pure sugar, right? So sucrose, if it's all sucrose, then it's pure, right? We could have elements that are pure, like sodium metal, pure sodium. Let's see, somebody's
Hey,
having.
Dr. Henry.
Yep.
I don't know if it's too early for a question, but I actually have to ask.
Okay.
Yeah, so you said a pure substance has only one stuff in it. So when I was studying my textbook, what I understood by a pure substance, like even a sugar and salt solution could be a pure substance. That's what I could understand. I stand corrected. So from your definition now, I'm actually confused. I want you to clarify that.
Something that is pure.
Yes.
Okay, so a pure substance, right? When we make reference to a pure substance, it basically means the simplest way of looking at it is that everything there is identical. They're exactly the same chemical formula. Like for instance, if we just have water, H2O, it's just water. It's pure water, right? Even though it's H2O, it's all pure water. It's pure. Okay. Now, if we have water and salt, that isn't pure, right? That's water and salt. Okay. So then that would be a mixture because it has two pure substances that are in it. Okay. Two or more. Okay. So when we make reference to a pure substance, it means that we only have one of that kind, right? And that's all you have in it. Okay. Okay. Good. Okay. So now let's see if you guys how well you guys are handling this, right? So if I have, let's say, water and oil, is that a mixture or is that pure substance?
Water and water.
Mixture.
A mixture?
Water and what?
Okay.
They don't go together.
Yeah, they don't go together, right? Water and oil, right? So, but it's a mixture because they're in the same bottle together and we can shake it up and all that stuff, but they're not thoroughly mixed together, right? And we'll talk about the difference between that. Now, if I have, let's say I had copper wire.
Pure. Yeah, a pure substance.
That's a pure substance. Okay, good. Okay, good. So you guys understand what pure substance is. So, how many of you guys cook?
Try.
Try to cook. Anybody cook spaghetti? Know how to cook spaghetti?
Yes.
Pasta?
Yes.
Okay. Okay, so everybody knows when you're cooking spaghetti, you add salt to the water before you get started. Why do you add salt to your water?
So it doesn't
The water absorbs into the pasta.
spill.
What? I don't actually know.
I always thought to give it flavor.
It's
I
flavors the
say
noodles.
for your noodles
But
not
it's
to
how
stick.
it's so that it won't clump
I was
up.
told that it helps the starch
Give the
to come
pasta
out.
flavor.
I love this class. You guys are
Doesn't
very,
it
I have a lot of great
increase the
ideas,
boiling
right?
point?
So let me see if I can recap some of
So
the
it's
things
not
that
to
were
give it
said. Okay, so didn't I hear? I said to give it flavor, to stop it from boiling,
Mm.
to what was the other one?
Stop it from like clumping up.
I said to
Stop it from clumping up,
Isn't
Yeah,
it to increase the
water.
boiling point
Yeah.
to decrease. So is it to decrease the boiling point?
or
to increase the boiling?
increase?
The water
Increase.
boils faster.
Yeah.
Does the water boil faster?
I don't
my
know.
God.
Every time I put salt in it, I feel like my spaghetti does the water doesn't go
It
over.
decreases the
and, like,
boiling point.
Okay, so the correct answer is, so of course, technically they're all correct, right? Because salt adds flavor to everything, right? That's technically true, right? Technically. But the reason why that we always put salt in water when we're boiling pasta is because we want to increase the boiling point. So we want the water to get higher in temperature than 100 degrees Celsius, so that when we put the pasta in there, it doesn't get all sticky and gooey, that it sits in there forever. So it helps our pasta, somebody had mentioned that, keep it from getting all sticky and gooey and overly cooked, right? Because nobody likes soggy pasta, right?
Heck
No, 12 minutes.
So here, this is basically showing you what's happening, right? So water boils at 100 degrees Celsius. So this is the boiling point. So by us adding salt to water, we make a solution, a salt water solution. And it causes the boiling point to actually go up. So it's no longer at 100 degrees. It's like at 110 degrees. So that means that the water is actually hotter. And so that means it's going to be cooking that pasta a little bit faster, so it doesn't have to sit in the water as long. And it also keeps it, as you say, keeps it from clumping together because of those electrostatic forces that are involved in it. Okay? And so we'll be talking about that. We'll be talking about the changes in boiling points as a result of us adding things to solution, right? But we kind of use this all the time. Like you guys use it for cooking. You guys have been doing chemistry, whether you like it or not, since like you were like 5, because I know that I started cooking pasta when I was 5 years old or something like that. Or at least ramen noodles, one or the other.
The pasta.
Okay, so you know, we've been doing chemistry. Now you're going to get to see how it all kind of plays together and, you know, why it kind of makes sense. And you're going to be like, oh, yeah, I knew that a long time ago, right? Okay, so let's talk a little bit more about those pure substances and those mixtures. Okay, so here we have pure bromine, right? So when we make reference to pure, it's pure. It's only bromine. So we only have bromine there. Here we have pure water. So all of those molecules in there are just H2O. They're water. They look like Mickey Mouse ears, right? So if we have a mixture, we have bromine and water. Now those two things are not reacting with each other. There's no chemical reaction going on. They're just kind of interacting with each other. Okay, so reacting versus interact. Do you understand the difference?
Mhm.
Yeah.
Okay, so in the case of reacting, you're getting a chemical change, a reaction happening, right? And so somebody's going to be exchanging something from another. In this case, these guys are not doing that. They're just interacting, okay? So in this situation, the first situation, we have a small amount of bromine and a lot of water. In the other situation, we have a lot of bromine and a little bit of water, right? Both of those are examples of mixtures, right? Those mixtures are going to behave slightly different from each other because of the amount of substances that are in each one. And if we compare them to the original, it's going to be a little bit different because there's interactions happening between those two molecules. They're not reacting, but they're interacting. You guys get that?
Yeah.
Mhm.
Okay, so let's talk about solutions, right? So we talked earlier about the water and the bromine solution, right? So that's a mixture. So there's two types of mixtures that you can have. We can have what we call a homogeneous mixture, where everything looks exactly the same. It's uniform in appearance, mostly, right? And almost uniform in properties, right? So you have uniformity through the entire thing, okay? So, and we also have heterogeneous. Heterogeneous means that it's not uniform, okay? So there could be a phase change, or there could be something different between the two, something visibly different. Homogeneous, homo, like homosexual means same, right? So same throughout the entire thing, homogeneous. Hetero means different, like opposite sex, right? Male, female. Heterogeneous means different, okay? Easy way to remember it. So now if we're talking about something being homogeneous, right? That means that, again, its appearance is thorough through the entire thing. So for instance, milk. Do you guys drink milk?
Yes.
Yes.
Okay, so when you look at milk, is it homogeneous or is it heterogeneous?
Homogeneous.
Homogeneous.
It's homogeneous, right? Because it looks all the same. Now, if we let the milk spoil and it gets all cloppy and everything like that, is it homogeneous or is it heterogeneous?
Heterogeneous.
Heterogeneous.
Okay,
Mhm.
yeah, because in that case, you can see kind of the cleared part of it, and then you see all of the milk that's clopped together and everything like that, the spoiled parts coming together, you know, so you can actually separate the two, right? So that's an example of homogeneous and heterogeneous, okay? So how many of you guys ever go out to diners or anything like that? I mean, not anymore because of COVID, but back in the day when we're able to go to diners and eat at diners, you guys do that? Anybody? Like,
Yes.
okay, so as a kid, what I would do was I would take the salt shaker and I'd take the big old thing of sugar that they'd have for coffee, which they don't do anymore, probably because kids like me, but they would have this huge jar of sugar, right? So I take the salt from the salt shaker, put it in the jar of sugar, and then, you know, put the top back on and everything like that, and then wait for people to come and put in their coffee, right? So I'm going to ask you, salt and sugar, is that going to form a heterogeneous or a homogeneous solution?
Homogeneous.
Homogeneous.
Homogeneous, because salt and sugar looks exactly alike. You know, as you're dumping that into your coffee, right? You're thinking, oh yeah, I'm getting this. I like, you know, a lot of sugar in my coffee, so let me put a lot of sugar in here. And then you taste it and it tastes all salty. What are you going to be?
Heterogeneous. Oh,
It's still homogeneous, right? But you're going to be a little salty, right? Somebody used that joke earlier, so I told them I had to steal it. So, okay, so that's an example of a homogeneous solution. Now, if I had salt and pepper, right, and I had a mixture, I had a thing of salt and pepper all together, is that homogeneous or is that heterogeneous?
Heterogeneous.
Okay, simple, right?
Yeah.
Okay, so let's get to the adult part of things, right? How many of you guys drink cocktails?
When I wasn't pregnant.
Okay.
I could have one right
Did
now.
you say when you were pregnant or when you weren't?
When I wasn't pregnant.
Okay, I'm like, okay, wait a minute. You get that little twisted there.
No.
Okay, so in the case of, let's say we have ethanol. Ethanol is the chemical form or chemical name of alcohol, ethanol. So if we have ethanol in water and we put it together, right? So is that going to be homogeneous or is that going to be heterogeneous?
Homogeneous.
Homogeneous.
Okay, so what about, what is it called, the drink? Have you guys ever, oh, this is bad. Let me see. I'm trying to think of have you heard of a buttery nipple?
Mm-hmm.
Yes.
Yeah.
Okay,
My
so
God.
at the top of a buttery nipple, right? So you have, I can't remember what the liqueurs are at the top of my head right now, but I know there's a little bit of Kahlua, there's a little bit of cream and everything like that. And so you get kind of layers and stuff, right? And at the top, you put a little bit of whipped cream. So is that heterogeneous or is that homogeneous?
Hetero.
Hetero.
Okay, so those are examples of heterogeneous and homogeneous, right?
Yes.
Okay, so this is just basically showing you that here, this is again with ethanol, drinking alcohol. So you can't tell the difference between the two by visually looking at them, even though that they are different. Now, the thing is that, let's say, how many of you guys make alcohol? Like wine, beer, whiskey, anybody?
Make it
Anybody
now.
want to learn?
It's
Make
easier
mixed
to
drinks.
buy it.
Yeah, it is so much easier to buy it, but it's so much fun to make. It's so much fun to buy it, and it's also a lot easier to drink it, right? So let's talk about alcohol, right? So in the case of alcohol, if you're making alcohol, initially you're going to get something that's going to be like 15%, right? So the yeast that actually is used to make it, it makes it to about 15%, and then it starts killing the yeast. Okay. So, but if we buy alcohol at the store, it's about 50%, right? So if we get 100 proof, that's 50% alcohol. If we get 40 proof, that's 20% alcohol. If we get 80 proof, that's 40% alcohol, right? So if I go from 15 to 50, right? So how do they do that? How can they go? Because, you know, it's only made to that concentration initially at 15%. How can they get it all the way up to 50%?
By adding more alcohol?
Well, if they use yeast and stuff to make it, they can only make it to
Isn't
15%.
it called like fermentation or something?
Oh, yeah.
Fermentation is the process of making alcohol.
Okay.
Okay, so, but you're treading down the line here. So what is a way that we can separate? Because if we think about that 15%, that means that 15% of it's alcohol. And that means that, what is that? 85% of it is water?
Oh, it's distillation.
That's right. Okay, because we can use the properties of each of those components, alcohol and water, right? Water boils at 100 degrees Celsius. Alcohol boils at, it's 89.04 degrees, something along those lines. Actually, 80.4 degrees. 80.4 degrees, alcohol starts to boil, okay? Water boils at 100 degrees. So if I wanted to get something that's pure alcohol, what I want to do is set up the boiling temperature at 80.4, right? So I get it right at 80.4, so that means alcohol will boil out of the water, and then the water will remain in solution. And then I just kind of get the alcohol vapors, and then I collect them and then cool them, and then I get condensation of pure alcohol, right? So that process is called distillation, right? We're using two different boiling points to sit there and separate two different chemical solutions, okay? Or chemicals, okay? So we can use properties of those chemicals to sit there and do separation. Like for instance, here if we have a mixture of iron and sulfur, we can separate iron and sulfur by using a magnet. So all we will do is we'll run the magnet over that solution, and the iron is going to bind to the magnet, where sulfur is a non-metal. It's not going to bind to the magnet. And so we'll be able to collect all of the iron and leave just the sulfur. Simple. And so we're using the characteristics, the fact that iron binds to magnet, which is a physical characteristic, to sit there and separate it from each other. Okay. So we just talked about distillation, and we can also do it by filtration. How many of you guys make coffee? Every morning I got to have my cup of coffee. Now, do you just throw your grinds in water and everything like that, and then you're good to go, drinking the grinds and everything?
No.
No,
because
you filter it.
we filter it, right? So you use a filter paper, you use gravity to sit there and let the water drip through. The water drips through, and you get your coffee solution, and you keep all of your grinds up at top, right? Pretty simple. So again, you guys have been using chemistry your whole entire life and not even recognize it, right? So this is a distillation column. This is a laboratory distillation column or distillation apparatus. So in this case, you have your solution that's being boiled. So in this case, water is going to be evaporated, and then it's condensed by using a liquid, basically a cooling solution like water, to cool it down. So the water comes in, the water vapor comes in, it gets cooled down, and then we get pure water on the other side. And then at the end of the day, we'll be leaving our other solution in the other side because we never got up to the temperature that it boils at, okay? here, this is an example of gravitational filtration or gravity filtration. So in this case, we use filter paper. We put the filter paper in the funnel, and then we have a solution that has a combination of solids and liquids. So we're able to collect the solids up into the funnel, and then the liquid is able to go into our beaker here. Okay, this is a funnel, this is a beaker, this is a rack or a stand. A ring stand. Okay, so let's talk about elements and compounds. So an element is basically a pure substance that can't be broken down to anything else. So you're broken it down to as far as it can possibly go. So for instance, if we just have carbon, chemical symbol for carbon is C. So if we just have carbon, that's an element, okay? Oxygen is diatomic, and there are 7 diatomic elements. I'll talk about those here in a minute, but oxygen is also an element, okay? Only thing, there's always going to be 2 of them around under normal circumstances. Okay. So a compound is a combination of 2 or more different elements. So for instance, if I have CO2, carbon dioxide, that's an example of a compound. 2 different elements together, okay? A molecule is 2 or more elements. Okay, so O2, is that a molecule?
Yeah.
Yeah, no, maybe?
Yes.
Yes.
Yes, because there's 2 of them,
Yeah.
right?
Yes.
Yeah.
There's 2 oxygens, so it's 2 or more. What about carbon here? Just carbon by itself?
No, it's just an element. Element.
Nope, it's just an element. That's right, because there's not 2 or more, right? What about CO2, carbon dioxide? Is that a molecule?
The molecule.
Okay.
Thank you.
Yeah.
Okay, so now a compound, like I said, is 2 or more different elements. Okay, so CO2, is that a compound?
Yeah.
Yes.
It is.
Yes.
What about this carbon here?
No.
No.
An element.
Okay, and what about O2?
Yes.
An element.
Basically, CO2 is a compound and a molecule, right?
That's right. CO2 is a compound and a molecule, but what about the oxygen? Is that a compound?
No, it's an element.
Element.
It's an element. Just by itself,
That's
it's an
right.
element, right?
That's right. It's an element.
It's a molecule.
diatomic element. That's right. And it's also a molecule, right? Are you with me?
Can you explain that just one more time?
So compounds are 2 or more different elements. Okay? A molecule is 2 or more elements. Carbon dioxide, CO2, is that a compound?
Compound.
Yes.
Compound. Yeah.
Is it a molecule?
Yes. Yes.
O2, is that a compound?
An element.
No.
Yeah. It's a compound and a molecule.
Is it a compound?
Oh, no.
An element.
It's a
Element.
molecule and an element.
It is a molecule and an element because it has 2 of them, right? A molecule is just 2 or more elements. It's 2, right? And it's also an element,
I
right?
have a question, Dr. Harry.
Yep.
So what's the difference between a compound and a molecule? If it's composed, both are of Composed of 2 or more elements.
Okay, a compound is 2 or more different elements. A molecule is 2 or more. Okay, so the difference is that word different. Compound, 2 or more different elements. C, carbon and oxygen, aren't they different from each other? The C and the O?
Yes. So it's a compound.
That's right. So it's a compound. Okay, it's also a molecule because there's 2 oxygens and there's a carbon. So that's a total of 3. Right?
Oh, okay.
Okay, where O2, it's a molecule, right? Because there's 2 or more of them. Because there's 2 oxygens, okay? And it's also an element. Okay? Are we good?
Yes.
Okay, good. Okay, so let's go to the periodic table real quick. So I told you that there are 7 diatomic elements, meaning that these elements, they exist as 2. Di means 2. Diatomic, 2 atoms. So there'll be 2 atoms together. So in their natural states, when they're normal conditions, they exist in 2s. So for instance, let me write it on the side here. We have, oops, I'm like, you guys don't see my periodic table, do you?
No.
Okay, how about now? I was like, where's that periodic table?
Not yet.
Can you see it now?
No.
There.
Yeah.
Yes.
There.
Yes.
Yeah, we can see the table.
Okay, good, good. Okay, so let's choose a different color. Orange, and we'll make it thick. There we go. That gray is not working for me. Can you see it now? Can you see my writing?
Yes.
Okay, so H2. N2. F2. O2. I2. Cl. 2. And Br2. So that's 1, 2, 3, 4, 5, 6, 7. Okay, so 7 diatomic elements. The way I remember it is have no fear of
Ice cold beer.
ice cold beer. So hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. Okay, so those are your diatomics. So every time that you receive them in a chemical equation, and they're a pure substance, just oxygen, right? It's going to be O2. Okay. Now, if it's in a compound like carbon dioxide, well, that one's O2. But let's say carbon monoxide, then it's only going to have carbon and oxygen. Mono means 1, carbon monoxide. Okay. So, but when we're talking about oxygen by itself, oxygen gas, we always write O2. Are you with me?
Yes.
Okay, good. Good, good, good. Okay, so let's go back to that mixture and compounds and all that good stuff. So mixtures, they're impure. And it makes sense because you have two things that are mixed together, two complete independent things that are mixed together, impure. Okay, so they can be separated by physical means. So we can use distillation, filtration, let's see, just their properties, their physical properties to sit there and separate. Okay, so when we separate them, we can end up with a compound, which is pure, or we can end up with an element, which is pure, or we can end up with both, you know, compound and an element. Okay, so a compound, the only way compounds can be separated is by physical means. So that means that things they're physically interacting with each other. So those elements are bonded together, not only physically interact, they're connected. So like for instance, H2O. That hydrogen and oxygen, they're forming bonds together, right? And they're connected. So the only way that we can separate hydrogen from oxygen is by a chemical reaction. You guys see that? Understand it?
Yes.
Yes.
Okay, good. Okay, so here we have a couple of items. So I want you to help me, right? So pennies, those old-fashioned copper pennies. Is that a pure substance?
Is it
The
just
old
copper?
pennies. What was
Yeah,
that?
it's just copper. Is it just copper?
It's just copper.
Okay, then it's pure substance.
It's a pure substance, right?
Yeah.
So the old pennies are a pure substance. Okay. What about, let's say, pencil lead? Lead is
It's
that
just
pure
pencil lead.
substance?
It's a pure substance.
It's a pure substance. What
Yeah.
about iron? An iron rod or an iron bolt?
It's a pure substance.
Substance.
Yeah.
Okay. What
Mhm.
about baking soda?
That's a mixture.
No, that's a mixture.
Compound.
There's lots of
Compound?
stuff in.
Compound substance.
So it's a compound. That's right.
It's a compound. Okay.
It's a compound. So yes, it's sodium bicarbonate. So that's
Sodium bicarbonate.
NaHCO3. Okay. What about chalk? Chalk?
It's a compound. It's a compound.
It's a compound. Okay. Okay. Simple, right? Not too hard?
Yeah. Yeah.
Okay, so let's talk about those abbreviations. So when we're looking at the periodic table, did you guys notice there's a certain way that the periodic table is organized and done? So let's talk about the periodic table a little bit more. So,
Yeah.
Mhm.
Okay, so we have sulfur here, right? So
Okay.
if we look at sulfur, it starts with the capital S, right?
Yeah.
Okay, so can you tell me what is the symbol for chromium?
CR.
Okay,
CR.
so I'm a new student, right? And if I see you said CR,
Okay.
is that correct?
Yes.
Yeah.
No, small r.
Ah,
Okay. CR. C small r.
yes. So it's C small r, right?
Yeah.
It's not C capital R. So some of the elements have two letters. Some of the elements have one letter. So if it's two letter, you always have a capital and a lowercase. You want to be sure to have a capital and a lowercase because it can mean two different things. Like for instance, if I go and write P-O, or I write P-O. What does this mean?
By mouth.
An abbreviation.
What does P mean?
Phosphorus.
Phosphorus and
Oxygen.
oxygen. So this
Okay.
compound has phosphorus and oxygen.
An oxygen. Okay.
And what about this one? What does that mean?
Hello,
It
something.
is an element.
Polonium. Polonium. Yeah.
Polonium,
So this is polonium and this is phosphorus and oxygen. They're not the same thing. And so you want to be sure that you're writing it correctly, because if you're not writing it correctly, you could have me adding the wrong thing and cause an explosion, right? We don't want that to happen. Okay?
Mhm.
So let's see how good you guys are at identifying the elements. Argon. What is the chemical symbol for argon?
AR.
AR.
Okay. What about francium?
FR.
F small m.
FR. Okay.
F small r. Mhm.
Yes. Capital F, small r.
Yeah.
Okay. What about europium?
UR.
What about, you said UR?
Mhm.
Are you sure? Europium?
You.
I'm not
Just
sure.
a U.
Europia?
Oh my God.
That's the moon, is it not?
Okay.
Capital E, lowercase u.
It's capital E, lowercase u.
Okay.
What about gold?
Gold.
Capital G, lowercase
Isn't
d.
it?
No.
Is that not
What was it?
AG? AG.
Gold is AG? Are you sure?
No, I'm not.
Lowercase d.
I can't see.
Capital G, lowercase d?
AU.
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 AU stole my gold, right? AU.
Oh, it is.
Oh,
AU stole my gold. Okay.
Some of us are blind.
yeah. We can't see it.
I have to get my book.
Okay. So you need to be familiar with how to find your elements, right? And so we use those symbols to sit there identify what element we're talking about. Also, the periodic table is kind of organized. On the side, these are called your periods. So going down here, that 1, 2, 3, 4, 5, 6, 7, those are your periods.
Mhm.
Going across here, those are your groups. Okay. Group 18, this group is called your noble gases. Group 17, these guys are called halogens. Okay. Group 18s are called chalogens. Group 19s are called your nitrogens. Okay. So you want to be familiar with where to find things at. Now, if you have a nice, beautiful periodic table, it's really easy to sit there and figure that out, right? So here on P table, if you run it over, let's say these are your nonmetals, right? Those are your noble gases. Those are your other nonmetals. Your alkaline metals. Your alkali metals. Your actinoids. Your lanthanoids. Your transitional metals. These are your post-transitional metals.
Pues van a ir a Las Vegas con nosotros el 19.
Are you sure? So who's been with us? Our metalloids. Okay. So the periodic table, like I said, is kind of organized. So if I'm asking you something like, okay, so group 14, period 5. So what's in group 14, period 5?
N.
SN,
So what is SN?
selenium.
No,
Okay.
Tin? I can't
it's
read.
10.
And
Yeah,
then
10. Tin,
Oh.
10.
Oh my God. Okay.
Okay. And you can't just assume, oh, it starts with an S, right? You can't assume that it's selenium because it started with an S, right? You can't make that assumption all the time,
Okay.
right? Like for instance, let's see, period 6, group 6.
Tungsten.
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 Yeah,
Tungsten.
Okay.
yeah, it starts with a W. Where in the hell did they get tungsten from, right? So you'll understand that some of the symbols, they actually come from the old names that they used to be called. Like, for instance, iron is Fe, right? Ferrous. Ferrous is what they're often in the old days, it was called ferrous.
Okay.
Right? So they use Fe for iron. Okay. Okay, so let's go back to chemicals. And there we go. Okay, so when we're talking about compounds and everything, so like for instance, we have hydrogen chloride, HCl. Okay, so HCl has 1 hydrogen and 1 chloride. The ratio of HCl is always going to be 1 to 1. So anytime that you're talking about hydrogen chloride, it's always going to be 1 hydrogen to 1 chlorine. Okay, water, H2O. So 2 hydrogens to 1 oxygen. It's always going to be 2 hydrogens to 1 oxygen, right? So if you see this, is that water?
No.
Okay, so we know that that's not water because it's not 2, 1, right? So barium chloride, 1 barium, 2 chlorides, okay? Okay, so an atom is going to be the smallest particle of an element. So smallest thing that you can get other than the subatomic particles, but we'll talk about here later. And we've already talked about a molecule. Okay, so when we're talking about water, so that relationship of 2 hydrogens to 1 oxygen. So this is the law of definite composition, right? Or the law of constant composition. So regardless of how much water you have, the ratio of hydrogen to oxygen is always going to be the same. Okay? So if I have CO and CO2, are these the same thing?
No.
No, they're not, right? The ratio between CO and the ratio between CO2 are different, okay? I know it's like straightforward and simple, but it's amazing how many people won't pick that up. Okay, so charges. How many of you guys get all charged up? Okay. Okay, so let's talk about these charges, right? So now we have what we call electrostatic forces. So electrostatic forces are basically forces that are a result of charges. So if we have a charge that's positive and a charge that's negative, what's going to happen?
They're going to attract.
They're going to attract, right? They're going to come together, okay? So opposites attract, okay? So if I have a positive and a positive, what's going to happen?
They're gonna
Repulsion.
repel each other.
They're going to repel, okay? So if I have a negative and a negative, what's going to happen?
They're going to repel from each other.
They're gonna what to each other?
Repel. They're going to repel each other.
They're gonna repel, right?
Yes.
Okay, so they're gonna go away from each other, right? So only opposites attract. Okay, so do you guys remember when you were in high school? Right?
Yeah.
And there's that boy and everything. You're like, oh, that boy, he is so cute. And he comes up to you and he says, hey girl, what's your name? And you say, I'm Mary, you know, right?
Yeah.
And you're like, and he's like, what you doing tonight? And you're like, nothing, right? And then you go home,
No.
right? You go home and you tell your mama, right? You say, mom, you wouldn't believe who asked me out on a date tonight, mom. You wouldn't believe it, right?
Okay.
You know, Billy Bob asked me out. And your mom says, who? Billy Bob. You mean Billy Bob Johnson? No. Billy Bob Johnson is a bad boy. His mama's bad, his daddy's bad, his brother's bad. He's just as bad as all of them, right? You ain't going out with him. Then what did you do?
Married him.
You married
Stay
him.
away. Stay away because your life's going to be hell.
Have kids with them.
You have kids with them. Okay, so exactly, right? Opposites attract, okay? So because those opposites attract, a lot of chemistry is about that, those opposites attracting. So those opposites are called ions. That positive and those negative charges, those are ions. They're going to be attracted to each other. And so I'm going to bring you, I'll give you a little bit of a head start on things. Okay, let's see if I can get this to work. Hold on. Oh my. Okay, on the periodic table, we have metals, we have non-metals. So all these guys are metals. These guys here are all non-metals. Okay, so I'm gonna ask you guys a couple of questions, and then I want you to be honest about it and everything like that. I know none of you guys are criminal or have a criminal thought or anything like that ever, or never stole anything. So I'm not saying that, right? But let's just use a little bit of logic and what kind of makes sense. Now, if you were, let's say if you were a criminal, now, would it make sense to steal your neighbor's bicycle, the one that lives right next door to you? Or would it make sense to steal the bicycle from the guy across town?
Oh, the guy across town.
Across town.
Okay. Why would that make sense?
Yeah, because you could easily be caught
He won't find you.
if it's your neighbor's bicycle.
Okay, exactly, right?
Yeah.
So the probability of the guy across town finding out that you stole his bike is a lot less than the person that lives next door to you, because the person that lives next door to you is going to be like, dude, you just stole my bike. What the hell, right?
Yeah.
Okay, so now these guys are all non-metals. So when non-metals come together and they form bonds, they form what we call a covalent bond. Covalent bond means sharing. So you're cool with sharing, and I'll write that out so you guys will know how to co. Okay, so covalent means sharing, right? So you're sharing, right? So you're cool with sharing. So if your neighbor sits there and says, hey, dude, let me borrow your bike, you know? And you're like, yeah, go ahead, borrow my bike. As long as he brings it back, it's all cool, right? So that's sharing, right? Okay. That's true, Cassandra. Neighborhood criminals typically don't think things through. Okay, so ionic bonds is about give and take. So somebody's going to have to give and somebody's going to have to take. Okay, so when you're here, when you're non-metals are going to share because they're right next to each other. They both are kind of greedy and they're going to share those electrons. They're not going to want to give them away. Where the metals and the non-metals, when they come together, one of them is going to give and one of them is going to take. Like, for instance, we're going to talk about sodium chloride. Salt, NaCl. So what happens is that Na wants to get rid of an electron. And you're going to ask me why Na wants to get rid of an electron, and I'll tell you this in a second. And chlorine is going to want to gain an electron, okay? So Na is going to become positive because electrons are negatively charged. So if you remove one charge that is negative from it, it becomes that
Positive.
atom becomes positive, right?
Okay.
Because everything on the periodic table has a zero neutral charge. Okay. As soon as you remove an electron from it, it becomes positive. Add up electrons to it, it becomes negative. And the chlorine is going to become negative. Okay. So if you have a positive and a negative thing, they're going to come together and be attracted to each other. Hey, baby, what's your number? And then they form a compound. So this guy is called an ionic bond. So water is a covalent bond. Salt is an ionic bond. Do you see the difference?
Yes.
So far? Okay.
Yes.
So now you guys want to ask me the hard questions. So why is it going to become negative? Why is it going to become positive? Okay, so now this is going to kind of deal with society. You know that term nobility, noble. Somebody is a noble. Oh, they're part of that noble class. What does that mean? What does that mean to you?
I'll say it means they are prestigious.
Prestigious, okay?
Yeah.
Anyone else?
I say high class. Same thing.
High class, okay. Upper class,
Important.
important. Okay, so can I ask you something? If you have the option of being noble or not being noble, would you be noble?
Yeah.
Yes.
Okay, okay. So if I was a prince of some country or something like that, and I come to you and I'm like, hey girl, or hey guy, what you doing? What's your name? Do you want to be my wife or husband?
Okay.
What are you gonna say?
No, you're not cute.
It depends.
Oh, I'm not cute.
It
What do you mean?
depends.
I am cute. What are you saying now?
It depends.
And then I said, well, I don't have to be cute. I got money, right? I got money. I can give you cars. I can give
have
you
my own money.
riches.
Well, I could buy myself a car.
Have a date for the wedding.
I
That's
could
why
buy
I'm working
myself
hard
a
to buy
car.
myself a car. There you go.
Exactly.
Oh, okay, I see how it is. So you guys are all, I'm independent, okay? I see how it is, that's fine. I'm gonna tell you, I'm not gonna lie to you, right? You come to me and you're a rich prince or princess or whatever, and you tell me you'll pay all my bills and give me a monthly allowance as long as we get married. Hell yeah! When are we getting married? Tomorrow?
Well, you're going to be useless.
I won't even blink twice.
You're about money.
I'll be moving in the next day, right? So
Wedding date.
okay, so nobility, right? So if we think about nobility, it's something that everybody wants to be like. Somebody wants to be like them, essentially, right? So you want to be rich, you want to be wealthy, you want to have those things. In a sense, it's stability. So these guys here are noble, right? So they're the noble gases. They're stable. They have everything that they need, that they want. At the end of the day, it's about stability. They want to be stable. Everything on the periodic table wants to be stable. It wants to have some stability. It wants to use low energy and be stable. So they want to be like the noble gases because they're there already. So they have a couple of ways to be like a noble gas. They could either be sharing electrons, they could be taking or giving electrons, okay? So those are your options, kind of like us, right? So why do you get married?
Companionship.
Companionship and stability, right?
Stability.
Yeah, nobody says, I want to marry the local crackhead, right? You may do it, but you don't plan on it, right? Right? And you don't plan on it because you know that the local crackhead isn't stable, right? So you're looking for stability in a sense, right?
Yes.
Okay.
Hey, if he's selling and making that money, you're gonna run to him.
I didn't say the dealer. I said the local crackhead. There's a difference.
Okay.
Okay.
Yeah.
Okay. This is going to be a fun class. I can already tell.
Mhm.
Okay, so now the way, as I said, the way that you get stability is either by giving up electrons, taking electrons, or sharing electrons. And so
Okay.
those are the type of bonds that you're going to have. When you're giving and taking, those are ionic. When you're
Okay.
sharing, those are covalent bonds. Okay.
Yes. Mm.
So, and believe it or not, the giving and taking is all about charges and attraction. Okay. And so that's why I wanted to kind of stress that.
Can you
Okay,
repeat
how are you
that
guys
again,
doing so
first
far?
again?
Pretty good?
You're doing good. Yes.
Good. Okay.
Yeah.
Okay, so let's see. Let's talk about a chemical formulas. Right, so right now, this is a chemical equation. So on this side, we have our reactants. So we have copper and oxygen gas. Copper plus oxygen gas, and this is called the yield sign. Yields CO2. Now you notice that we didn't put an equal sign, right?
Okay.
It's a yield sign. It's an arrow going to the other. So that tells us that the reaction is going in that direction. So this plus this equals that. So we could do it with like a, how many of you guys bake cakes? Who bakes cakes? Box cakes. Any
Yeah.
Okay.
Just a look amount.
So if we bake a box cake, it's eggs,
Milk.
milk,
Butter.
Butter.
butter. Oh, you guys are
Flour.
like me.
Oil.
Oil
But isn't the butter oil?
Why would you use oil?
or water.
Water?
Butter or oil.
Oh, butter or oil. Okay.
Okay.
And a cake mix, right?
Yeah.
Yeah.
And then we're going to get a cake.
Mhm.
Okay. Now it's eggs plus butter plus milk plus water plus a cake mix, right? So that's the same thing that we do for our chemical reactions. Copper plus oxygen is going to make copper. I mean, not copper. Carbon plus oxygen is going to make carbon dioxide. You guys get it?
Yeah.
Okay. So the other thing is, chemistry is all about the law of conservation, right? The law of conservation basically says, and we will boil it down really simply, what it simply says is, what you put in, you must get out. Okay, I'm gonna say it again.
Okay.
What you put in, you must get out. So, how many carbons do I have over here?
One.
One.
Okay, so I have one carbon. How many carbons do I have on my product side?
One.
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 Nice.
Okay, how many oxygens do I have over here?
Two.
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 And then how many oxygens do I have over here?
Two.
Two.
Okay, so what I put in, I got out. So that tells me that I have a balanced chemical equation. Because what we put in, we have to get out. Okay, again, the law of conservation. Okay, so let's go down here. So we have 2. So this number here represents a coefficient. That means that we have 2 water molecules. So we have H2O and H2O. So that's what that means. Okay, so the coefficient means that we have 2 water molecules. Okay, so 2 water molecules, if we break that down using a chemical reaction, we're going to end up with 2 hydrogen gas molecules and 1 oxygen gas molecule. Okay, so if we look at it to see if it's balanced.
It is.
Okay, how many hydrogens do I have all together?
4.
4.
Oh, 4.
Two.
Okay, how many oxygens?
Two.
Two,
Oh,
right?
two.
So,
Yeah.
right, 1, 2, right? Okay, what about over here? How many hydrogens?
Four.
Or
Oh, 4.
How many oxygens?
Two.
No.
4.
Okay, so since this is an understood 1 in front of it, there's only 2. Okay, you guys get that?
Yeah.
Okay, now you say that, okay? So we're gonna test your skills. You guys ready?
Mhm.
Okay, so you guys, how many of you guys breathe? Anybody not
Breathe.
Breathe.
breathe?
We all do.
Okay. I would hope you all do. If you don't, then that's a problem, right? Somebody's good.
Yeah.
Okay. So if you breathe, you're doing cellular respiration, right? So you're basically breathing in oxygen to help break down the sugar. Okay.
Yeah.
So that you can get some energy out of it. So the chemical formula for that is, see, glucose is C6H12O6. Plus O2 yields CO2. So you breathe out carbon dioxide and you go tinkle and water. Okay, so those are your products. Okay, so this chemical equation isn't balanced. Let me show you why it isn't balanced. Okay, you guys got to help me out though, because I'm old. So on the reactant side of the equation, how many carbons do I have?
6.
How many hydrogens?
12.
Oh,
How many oxygens?
8.
6. 6.
Are you sure? I heard 8
6.
and I hear 6. There's 6 here and there's 2 here.
Oh, 8.
Oh, 8.
Oh my God. 8.
Okay.
Yeah.
So on our product side of the equation, how many carbons?
1.
1.
How many hydrogens?
2.
2.
How many oxygens?
3.
3.
Okay. So if it was a balanced equation, what we put in, we should have gotten out. So we get 6 carbons. Did we get 6 carbons over here?
No.
Oh.
So it's not balanced.
No.
So the next job as a chemist, we're going to balance the chemical equation, right? So the way that we do that is, how can we make it so our product side has 6 carbons?
6 in front of this carbon.
Okay, so we're going to put a 6 in front of here. So then let's cross this out. And now we got 6. So how many oxygens do I have now?
12.
That's 12 plus
13. Well,
13. Okay. So now is it balanced? Is everything balanced? So our carbons are balanced. Now what about our hydrogens? Are they balanced?
no.
Okay, so how can I balance my hydrogen?
Add a 6.
Okay, so you're saying put a 6 here?
Yes.
So that would give me how many hydrogens?
12.
No.
Okay, so then how many oxygens do I have?
8.
8.
6 times 2
12.
plus 18.
18.
Okay. Okay, so we have 8 and 18. So this is a problem, right? Because over here we have 8, but both of these guys are balanced, right? So I know I'm not going to want to touch this since it's already set up. So what can I put? What number can I put in front of here so that I would have a total of 18 oxygen?
5.
5? Are you sure?
6.
You could put 2 in front of sugar or
No, Mary, because look, our carbons are already set up. So why would I put 2 in front of us?
And then you could just manipulate it. So that's what I was thinking.
No, you don't want to just manipulate it. We want to think logically, right?
Okay.
Okay. So these guys, the carbon and the hydrogen's already set up. So if we put a 6 in front of this oxygen, this O2, that gives me a total of how many oxygens?
Okay, 12.
That's 12
Yeah.
plus the 6 that we got over here.
Oh, wow. Yeah.
So that's 18, right?
Yes.
Okay. So then both sides are balanced. Okay. Simple?
Okay.
No.
I have a question.
Yes.
Okay, so you could put 6 in front of the oxygen. So why didn't you touch the sugar? Oh,
Because the sugar is already balanced. The carbon, we have 6 carbons here,
okay, okay.
and we have 6 carbons there. So you
Okay,
don't want to, if it's not broken, you don't want to fix
Okay.
it, right?
Okay. I was just wondering, I thought that it was kind of a rule that I can't touch the sugar or something. I was just
Okay.
wondering.
So
Yeah.
an easy way to remember the chemical equation for cellular respiration is sugar is the devil. Sugar, 6, 6, 6.
Okay.
Okay? Questions? Okay.
I'm not gonna lie, I got lost.
Okay, no, that's okay.
Me too.
It seems like everybody else kind of got it, but I didn't.
No, I didn't get it either. You're not alone.
Can you do another example?
I
Yeah,
got lost
sure.
when you were adding like the second part from the, okay, I have 12, like you just like want to just throw it in and add it, or that's where I got lost.
Okay. Okay, so let's start. Let me go to a whiteboard and then we'll do another problem. Okay, whiteboard. Okay, so always start by writing down what you're looking at. So all of your different elements. Okay, then you say, how many do I have on each side? How many carbons do I have on my reactant side?
1.
How many hydrogens do I have on my reactant side?
4.
Okay,
How
so
many-
that number in the
2.
bottom means how many of the H you have?
That is correct.
Okay, okay.
And the number of oxygens I have,
2.
It's 2.
okay? Now on my product side, how many carbons?
1.
How many hydrogens?
2.
And how many oxygens?
3.
Okay, so is carbons balanced?
Yeah.
Okay. What about our
Imbalance?
hydrogens?
No.
Imbalance.
Okay, so we need to balance our hydrogens. How would we balance our hydrogens?
Add it to.
Add 2 in front of H2O.
So we'll add a 2 in front of it.
That's right. Because
Why
that's
in
a
front of it?
coefficient. Because it's a coefficient. That means that you're going to get 2 water molecules, right? So once you have the chemicals there, you don't want to change the chemical. So the rules of balancing equation are you never want to change what that chemical is. If it's water, it's always going to be water. You can't make it hydroxide or,
Okay.
okay?
Mhm.
So it's like saying you have 2H
So then
squared,
times 2 would be 4.
right?
So, okay.
Yeah, so you're saying like, yeah, so you're basically saying I have 2
2
hydrogens, right? So 2 times 2
is
is
4.
4, right?
Oh, that makes
Okay.
sense. Yeah, okay.
Okay, so then now we have, let me cross mine out. We'll cross it out in red. Now we have 4 hydrogens. So 4 and 4. So 4 is what we put in and 4 is what we got out. So that's good. So now how many oxygens do I have?
4.
8.
3. So we need
How many
You
do I
have
have?
8.
Oh.
4.
I have
Okay,
4.
4.
Okay,
Yeah.
so now I have 4.
So now we have to add a 2 in front of the other side.
That's right. And we want to put it directly in front of the oxygen. Right?
Okay, I see. Now we have 4.
And now we have 4.
Okay, got
But
it.
why did you change the 3 to a 4? I thought you said you had to balance it, so that would mean that the 3 you would have crossed it out to make it you would subtract 1 to make a 2, right? So it can be 2.
No, because there's no subtracting, right? You're only the only thing you can do, right, is add. So we have, look at it here, right? We have to recount it. So since we had our hydrogen balance, we have to recount how many oxygens we have now, right? So we have 2 times 1. 2 times 1 is what?
2.
2.
Okay, so there's two oxygens over here. Okay, and then how many oxygens do I have over here?
2.
Okay, so 2 plus 2 is what?
4.
4. So now we have 4 of those.
Oh, okay.
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 Wait, Dr. Henry, just to clarify, the big numbers are coefficients and then the small ones are
Subscripts.
subscripts. Gotcha.
So you could only change the coefficients, you can't change the subscripts?
That's right, because the subscripts tells us what that chemical is. We know
Okay.
water is H2O, right? So that subscript lets us know that there's 2 hydrogens in water.
Oh,
you understand?
okay. Yeah.
And if you change the subscript, you're changing the chemical.
Oh, I see.
Okay.
Okay, so you don't change the subscript, but you change the other one. What did you say the other one that you changed?
Coefficient. The coefficient tells me that I have 2 waters here, right? So I get 2 waters from this reaction. It tells you how many of that molecule you have.
Okay.
Okay.
Mm.
Okay. How are you doing so far?
Good.
Doing great.
Okay, I have one more thing. So let's say we had something like this. Okay, so when we're talking about, let's say compounds, if we have parentheses and another subscript out here, this tells me I have 3 of whatever's in my parentheses. Okay, so how many aluminum do I have?
2.
Okay, so I
1.
have 2 aluminum. 2, right?
Oh, yeah.
Yeah.
Okay, how many sulfur do I have?
3.
Like an exponent, right?
That's right. And how many oxygens do I have?
12. 12.
Okay, you guys get that?
Yes.
Get 12. Right?
What was that?
How did you get 12? I thought you said that the little number on the bottom.
You multiply the 4 and the 3.
Oh, okay, yeah,
Because
yeah,
you
yeah.
have 3 of whatever's inside.
That's right.
Okay, okay, yeah,
Okay, questions,
yeah. No.
concerns? Cash.
Wait, how did you?
We're gonna go bald.
So can you
How did you
do
get-
the Al2 plus SO4 plus SO4 plus SO4? Or
No, because this is the compound. So you would never write it, because if you write it plus, if you write Al2 plus SO4, then it's something entirely different. You're saying I have aluminum, I have sulfur, and I have something else, you know? Do you understand what I'm saying? Where this here, this compound is called aluminum sulfate. So if I'm talking about aluminum sulfate, I have to write it like this.
Dr.
Okay,
Henry, how
even
did
though
you?
it's made up
How
of
did you get?
aluminum. Oh, go
How
ahead.
did you
I'm sorry.
get? How did you get 2 aluminums if it's subscript L or I?
No, it's Al.
Al subscript 2. How did you?
Al2. That means there's 2 aluminum. So this compound has 2 aluminums in it.
Isn't the 2 supposed to go in the front? as a coefficient or?
No. So I'm saying, so this lets me know that the compound, right? So when it's all together, there's two aluminums that are in that compound, okay? So I'm just breaking it down to tell me, like, if I'm trying to keep track of, I'm keeping a tally, right?
Okay.
It lets me know that I have two aluminums in this compound. That's what I'm writing down here.
All right.
Do you understand?
Yeah.
So
thank
let's
you.
say, for instance, I'm doing this chemical reaction. Let's do. So if I'm doing this chemical reaction, Mg plus Al2 yields Mg SO4. Oops. Hold on 1 second. Fix this up so it looks together. You guys understand that these are together. Okay, so, and on our reactant side, we have Mg. Okay, so
Yeah.
is this equation on the other side? How many magnesiums do we have?
One.
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 How many aluminum do we have?
One.
Two.
One.
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 Okay.
Okay, how many sulfurs do we have?
4. No, 1.
One. Sulfur.
Okay.
And how many oxygens?
4.
Oh.
Four.
Oh.
Okay,
Okay.
is it balanced?
No.
It's not
Oh,
balanced.
it's not in parentheses anymore.
Mm.
Okay, so we need a balance.
First one
right?
is.
What was that?
Magnesium is balanced.
So magnesium is balanced, so we're gonna leave that one alone for right now. Okay, what about our aluminum? How can we balance that out?
No.
You have to put the 2.
Could add 2 in front of the aluminium.
Okay, so we need to put a 2 in front of the aluminum.
Yeah.
Okay, let me move my plus signs. Give me enough room to write my 2 in front of there. Okay, so we got a 2 here. Okay, so then that gives me 2 on this side. Okay,
I have a question, Dr. Henry.
yep,
On the aluminum, the Al2 on the left, because that
Yep.
still means 2,
That's
but
right.
on the right side, you didn't make it a subscript. You made it just be 2 of them. What's the
that's right.
difference?
Because aluminum in its natural state is not diatomic. And so what you're doing is, okay, so you guys understand, you don't take it the way it is completely over here and just separate. That's not the way it works. They have to be in their natural states. So aluminum is a diatomic. What are your diatomic elements? You guys remember? There's 7 of them.
Have no fear of ice cold beer.
Have no fear of ice cold beer. Nitrogen, hydrogen, oxygen, fluorine, chlorine, bromine, iodine, right? So those are the only 2 that are going to have subscripts 2 when they're by themselves. Aluminum is only going to be aluminum, Al, when it's by itself. Only when it's in a complex, it's going to be in a complex with a certain number, depending on the complex it's in, okay?
So Dr. Henry,
Yep.
what I get now is that this is the way the reaction is designed. We have to understand that this is the way the reaction is designed, not dealing with stereotypes and all that kind of stuff like why it's 2 subscript, why it's 2. We have to understand that this is how the reaction happens and this is how the compound is.
Yes.
What you're saying. Okay.
Yes, and so at the end of the day, so the aluminum, Al, this tells me that I have the reaction here is going to give me 2 aluminums in this case,
Yeah.
since we have a 2 in front of it. Although it may change. We haven't finished balancing the equation yet.
Okay.
Okay. So
Yeah.
you need to pay attention to what the reactants are and what your products are. Your products
Yeah.
are. And then you want to balance it because you need a balanced equation to get it. Okay. And so
Yeah.
subscript, anytime that you see a subscript, right,
Okay.
that means that there's 2 of those in that compound,
Yeah.
right? If you
Yes.
see a coefficient, that means
Yeah.
there's 2 independent. of those,
Yes. Yes.
Okay. So
Yes.
does that help, Michelle?
Oh, yeah, but I don't understand why there could, I get what you're saying. But if there's 2 over here on the left, because Al2 subscript 2 still
Okay.
means there's 2 aluminums. And this
Yeah.
side means there's
Wait,
2
wait,
aluminums.
wait. So no, it doesn't mean that there's 2 aluminums. It means that there's 2 aluminums in that compound.
Okay, got you.
Okay. And then here, this means that whatever you did to this compound, you broke up those 2 aluminums, so they're free, so they're independent of it, right? So
Okay.
this, they're all together. All of this stuff is together,
You?
okay?
Question mark.
Okay, so our next part, how many sulfurs are we balanced?
No.
No.
Okay, so what do we need to do to balance our sulfur?
Add
You
it.
have to add a
Add 3,
in front of the,
Three.
the Mg magnesium tetrasulfate. Yeah.
Okay, so we added 3. So that gives me 3 of these guys. And now I
Mhm.
have
3 magnesium.
magnesium. Okay,
Yeah.
we'll go
so
back
on
to
the
that here.
right and magnesium SO are together?
Yes.
Okay.
And there's also 12 oxygen.
Okay, so then how many oxygens do I have?
question,
Dr.
Henry.
12?
Can be the 3 in front of the S instead of the Mg.
What?
Okay, because it can't be a 3 in front of the S because the coefficient goes in front of the compound. Remember, these guys are combined together.
Because S is not
Combined
alone.
compound. This tells me that I have 3 of these. So literally what I'm saying is I have Mg, SO4, Mg, SO4, and Mg, SO4. So I have 3 independent Mg, SO4. If you put a 3 in there, right, you're saying something entirely different, and it would be incorrect.
Makes sense.
Okay?
Mhm.
And just to clarify, the way that you got that 12 for the oxygen, it was because of the 4 times 3, right?
Yep.
Okay.
So then do you
Okay.
have to add 3 to the first magnesium on the left?
That is correct.
Yes.
Mm.
Okay? So what we put in is what we got out. Simple?
Yeah.
It's getting there.
Yeah.
Yeah.
Okay, that's good. See, you guys are already ahead of the game. So you're already learning how to balance equations. So when we actually get to that topic, you'll be like kings and queens, right?
Mm.
That was the equation.
Amen.
Do we leave it like this?
Yep. What you have up top, that will be the balanced equation.